Use algebra. What is this? An algebra exam? I mean, yes it is. So let's use that to show that this graph, which has half of the alphabet in it, A, B, and C, well, 3/26 of the alphabet, and X and Y, so 5/26 of the alphabet, where C cannot be equal to 0, crosses the x-axis at two distinct points. So something like that. Right? It's a parabola, right? A quadratic graph crosses the x-axis at 2 points. So it's not like this or like this, where it crosses 1 point twice, because those points are not distinct. Has to be something like that. It does say use algebra, but I think let's start with the graphical argument, because it might make a bit more sense for most of you. So again, we have a quadratic. Just focus on these bracket terms here. Will it be a positive parabola like this, or a negative parabola like this? So what tells us if it's positive or negative is the coefficient of the x squared term. And in this case, if we expanded, we would get a positive x squared. So that means it's going to be a positive parabola. Okay, so let's start with that. Y is a positive parabola, as x squared has a positive coefficient. Great. So we know it's going to look something like this, right? It's positive, it's happy, it's smiling. Now, that could mean that it's up here, right? However, we are given A and B, minus A minus B, which means, so since it is of the form x minus A, x minus B, so ignoring minus c squared for a second, it has two distinct roots. So that assumes that A is not equal to B, right? Because if they were, then they wouldn't be distinct. But let's assume they are distinct. Cool. And now, finally, there's minus c squared. So when you add or subtract a number from a graph, right, it shifts it in the vertical direction. So if we subtract a number, it will be lowering it like this. And so since c could be a negative number, but since we square it, c squared is always positive, and then we're subtracting that, it's telling us that we will always only lower this graph. It's never going to get higher. If it got higher, it might not have some roots, right? No roots here, no intercepts. But if we drop it and go lower, there will always be these two roots here. Of course, they'll change as you take it lower, but there will always be two distinct roots. So we could say c squared must be positive, because the square of a negative number is still positive, which leads us to say that there will always be two distinct roots. And so we've justified, purely from our knowledge of parabolas in the graph of this quadratic, that there will be two distinct roots, right, or x-intercepts. So that's one method. It will get you full marks. It might make a bit more sense to some of you, but let's show it graphically. algebraically. All right, so when it says things like no real roots, or one repeated root, or two distinct points on the x-intercept, we should be thinking of the discriminant. And if there are two distinct points, that means the discriminant must be greater than 0. So if we can characterize that or show that, then we've shown that this quadratic has two distinct roots. So to use the discriminant, we need it to be in general form. Right now it's in like factored form. So like it's factorized, but then it's shifted a bit. So let's expand and group like terms. Let's just rewrite that out. X minus b minus c squared. Let's expand the brackets. So x squared minus x minus bx. So the constants come first. Minus ax plus ab minus c squared. And I will group that into the x squared, the x, and the constant components. So the x component will have minus a plus b. So again, I just factored out an x as well as a negative sign. We could also just do plus and then have negative a minus b. That's also fine. But whenever possible, I like to reduce the number of minus signs. So there we go. That's equivalent. And then, of course, this is just our constant. So I'll use brackets to make that clear. So we have our a term, which is 1, our b term, don't forget the minus sign, and our c term, don't forget the plus sign. And we can then substitute that into the discriminant. So b squared, so big brackets, minus bracket a plus b, bracket, lots of brackets, but that's to include the negative sign there, squared, minus 4 times a, which was 1, right, the green highlighted bit, which is implied 1, times c, ab minus c squared. Now we can expand, simplify. So here, when we square a negative 1 times negative 1, so it's implied there's a 1 there, becomes positive, and then we're left with a plus b squared. Over here, we'd have negative 4, right, just negative 4 times 1, negative 4. You could do a few more steps here, but I'm just showing all my working. Expanding out these first brackets, a squared plus ab plus ba, which is ab, plus b squared minus 4ab plus c squared, right? Negative times a negative. Group like terms, a squared plus 2ab minus 4ab minus 2ab plus b squared plus c squared. All right. Oh, I hope you caught my mistake. I almost missed it. When it's in this line, if you didn't see it, you were probably yelling at the computer screen. I could hear you. So I forgot the 4. So that's minus 4 times negative c squared becomes positive 4c squared. Yeah, otherwise that stays the same. And now, okay, we're here. That's great. We've grouped all the like terms. Sometimes in these situations, we can actually factorize, like to simplify it further, which comes with practice, unfortunately, but that's what we're doing now. So looking at these first three terms, we see the middle term is a 2. The other terms have a coefficient of 1. So this actually factorizes to a minus b squared. So that's difference of squares. I forget the name actually. I should probably know that. But we can check, we could expand that out. We'd get a squared minus 2ab plus b squared plus 4c squared. So again, we use the discriminant. We used a, b, and c in terms of a, b, and c. We expanded group-like terms, and then we acknowledged we could factorize one more step. And so we did that. And remember, for there to be two distinct points, this discriminant must be greater than 0. Now, just reasoning about this first one, a minus b, that could be negative, right? It could be positive, we don't know. But since it's squared, a minus b all squared is strictly greater than or equal to 0. Right? And now c squared, well, we know even if c is negative, since it's squared, that is positive. And in the question, they actually said c cannot be equal to 0, which means 4c squared must be strictly greater than 0. Therefore, the sum of those two components must also be greater than 0. Right? If a minus b squared is equal to 0, that's fine, because 4c squared is still greater than 0. Therefore, two distinct roots. So just to recap this one, we have a quadratic equation, which we expanded and simplified, right? We grouped the terms into x squared, x, and the constant, so that we could then use the discriminant, which we had to do a little trick down here. When we got this expression, we could factorize that to simplify it. And then we said that that discriminant expression must be greater than 0 for two distinct roots. And then we reasoned that each term, well, the a minus b squared is greater than or equal to 0, and then the 4c squared is greater than 0, as c cannot be equal to 0, as specified in the problem, hence two distinct roots.